Swayam Prabha. Digital India. Educated India.
So, so to continue with what I was trying to tell you last time, see, we are now trying to try to put to use this definition of curvature that we have given. So I have already told you what is the formal definition of curvature of a curve. You take a curve, first of all it should be regular, then you put the condition that you take a regular curve which has unit speed parametrization. So I explained to you at length in the last two lectures why this constant speed, unit speed is a very natural thing, both in a physical sense and also in a mathematical sense. Okay, and then if you take a unit speed parametrization of a curve, measure the acceleration, that is second derivative, and measure its magnitude, that's your curvature. So that's the definition. Now the point is once you make this definition, the nice thing about this definition is that it's well made without any ambiguity, which is what a definition should be. But then the point is that you should extract something out of it, for example, a formula, and and whatever you get out of it should agree with what we already did. Okay, mind you, we have already defined and we have already got hold of the formula for curvature using geometric ideas, and that should kind of coincide with what you get from this definition. Okay, so we have to do this. So but the problem is that there is another question that we have to answer. The question is, why is it that a regular curve admits a unit speed parametrization? See, a regular curve means what? It means that there is the tangent vector, which is the velocity vector. Okay, geometrically the tangent vector to the curve at every point. Okay, which is the velocity vector. That velocity vector should never vanish. That the velocity vector never vanishes is the same as saying that the speed is never zero, because the speed is just the magnitude of the velocity vector. So you are taking a curve which essentially is regular, which has a regular parametrization, which means that it has a parametrization for which the velocity vector never vanishes. That is the same as saying it's a curve for which the parametrization is such that the speed never vanishes. But the question is, I want further a unit speed parametrization of that. Only after I have a unit speed parametrization of that, okay, then I can measure the acceleration and call that the curvature. Now the question is, why should such a unit speed parametrization exist? Okay, and see, already you may start with the parametrization which is regular, which only gives you that the speed is non-zero. It doesn't give you that the speed is constant and it's equal to 1 or something like that. So what you have to do is you have to reparametrize. You should show that there is a way of reparameterizing the curve. That means there is a change of variable you should be able to make, so that in the new parametrization or the reparameterization, your speed is equal to 1. So you have to show that such a thing exists. Okay, so I was trying to explain what this reparametrization is all about. So in general, I gave you one example where parametrization can go wrong. So the example that I gave you, let me just recall. So that is the starting point of this. So if you take our good old parabola, okay, then you know that the parametrization is given by 80 squared comma 280. Okay, and then it is, of course, this is a regular parametrization, because if you take the velocity vector, you are going to get 280 comma 2a, which is by differentiating with respect to t. And because of this 2a, which is not 0, this velocity vector is not 0, so it's a regular parametrization. But the parametrization can go awfully wrong if you use a different substitution. So for example, I said you just put t equal to u squared, then you are in trouble. What happens is that the new parametrization, you see that there is because I have put this u square, the derivative with respect to u of u squared is 2u sticks because of the chain rule, and then the problem is that this vanishes at u equal to 0. Therefore, this new parametrization of the same curve, the problem with that is that it's not regular. what has happened is that at the origin, you got zero velocity. Okay, that means speed is also zero, so it's not a regular parameterization. That's one issue. The other issue is, see, whatever we want to do, we want to also be able to undo it. So this change of variable is supposed to be it's a fair two-way thing. Okay, when you change a variable from this to that, okay, you should also be able to change from that to this. This change of variable cannot be one way. A proper change of variable should be able to work in both ways. So if it is going to be working in both ways, first of all, you must understand that this must be a bijective correspondence. So it should be a bijective map. So what happens here is, you see, this u going to t equal to u squared is already not bijective, because you see, plus u and minus u both go to the same t, which is plus or minus u whole squared is u squared. So first of all, it's not bijective. Then the second thing is, of course, that this function itself, t equal to u squared, if you differentiate with respect to u, you get 2u. Then the problem is that 2u vanishes at u equal to 0. So the derivative vanishes. So what I was trying to impose and just try to at least sell the idea last time was that if it is a decent parametrization, you want a parametrization which is bijective. You want it to be differentiable in both directions. Okay. So what is happening with t equal to u squared is, in one direction it's already not bijective, first of all. And the other thing is also happening, that the derivative vanishes. See, why we are worried about the derivative is that if the derivative vanishes, then you see the velocity vanishes, and then your regularity is lost. Once the velocity vanishes, the speed also vanishes, and you're in trouble. Okay, because we need to stick to unit speed curves, and in particular, speed can never vanish. So this kind of substitution is wrong. You could try to cure it by putting t equal to u cube. So but then again you will see a problem. So let me go to that. So you see, so suppose I try the following parametrization. Suppose we try, so I will put it as reparametrisation. See, suppose we try t equal to u cube in gamma t is equal to at squared, 2at. Of course, this is regular, of course, okay, but you are trying to reparameterize. When you do this parameterization, what happens is that you get a new parameterization in terms of u, which is just put t equal to u cube in the old one. So this is just gamma of u cube. So what you will get is, you will get a u power 6 to a u cube. You get this. Okay. Now what about this parameterization? The problem with this parameterization is, see, when you put t equal to u squared, the problem was that first of all you are getting only one half of the parabola. The second thing was, it was 2 to 1. It was not bijective. The third thing was the derivative vanishing. Now things are slightly better. What has happened is that, because this t equal to u cube, if you try to invert the function, you will get u equal to cube root of t. And the cube root of t, there is only one real cube root of t. So if you are working only with real numbers, okay, and you are not considering the complex cube roots, then the inverse function is nicely defined. So it is actually bijective. So here what is happening is, so you see the picture is like this. You have R, and from R to R2, this is the R2 is your original gamma, which is t. Let me draw it a little bit bigger. So this is your original gamma, and this is t going to gamma t, which is equal to at squared, 2at. Okay. Now what you are doing is that you are making this reparametrization, and you are just sending u going to t is equal to u cube. Okay. And now what is happening is that you take this composition. This is your new parametrization. This is gamma of u. Gamma is gamma of u. Here the original thing was small gamma is small gamma of t. Okay. Now this is, in this new parametrization, what is the nice thing? The nice thing is that, you see, this part is bijective. The reason is because there is an inverse. I can take t and simply send it to real cube root of t. That is well defined. So this is a nice bijective map. Okay. But again, what will happen is, look at, I told you it's not just enough to have a bijective map. What you want is that you want also differentiability in both directions. Okay. Of course, in the forward direction, what is this gamma u? It is going to be, as I have written here, it's going to be, au6 to au cube. This is obviously differentiable, because they are both components are actually polynomials, right? But if you take the inverse map, okay, there will be a problem with, if you just look at this one, okay, t going to cube root of t, there's going to be a problem with that inverse map, because the cube root is not differentiable at the origin. Okay, if you take the left derivative and the right derivative of the origin, you will get into trouble. So it's not differentiable. So what is happening is something nice is happening here. You have a bijective reparametrization, but it is still not a good reparametrization, because you see the differentiability is lost for the inverse map. Okay, and therefore what it means is that this change of variable is not an invertible differentiable change of variable. When you go from u to t, everything is nice. But if you try to come back from t to u, there is a problem. You cannot undo it. Because when you try to come back from t to u, you are ending up with a function which is not differentiable at the origin. Therefore, this is the issue. We don't want this kind of a issue to happen. So I am trying to push the fact, the following definition, that a reparametrization should be one for which you have a bijective map and it is differentiably invertible. That means the forward map, because it's a bijective map, there are two maps. There's a forward map, there is a reverse map, which is the inverse map of the forward map. And in both directions, it must be differentiable. Okay, so that is that should be the correct definition of a reparametrization. Okay, so this is just to motivate the definition. So here is a definition. The definition is a reparametrization of gamma of t. Okay, t belonging to, let us say, open interval AB, which is an open interval in the real line, is a function. So I am going to substitute t is equal to gu. Okay, I am writing t as a function of u, but now I will require that this function should be bijective, and both ways it should be, the function and its inverse must be differentiable. So let me write it such that this is of course for u varying from c to some d, let us say, on the real line. Okay, such that dt by du and which is, by the way, dt by du is nothing but g dash u, and the inverse, namely so you see, if you write t equal to gu, then this is also u is equal to g inverse t. Okay, so it means that the function first of all should be bijective. So and so let me write this. So g is bijective. So g is bijective, so I can write g inverse, and d by dt of g inverse t, okay, which is du by dt if you want. Both derivatives should exist, and let us follow this convention that whenever a derivative exists, you better require it to be continuous. We don't want a derivative which is not continuous. Okay, so here I will put that g dash. See, g is a function on c comma d, so I want g dash to be continuous on c comma d. First continuous on c comma d. Okay, so let me write it. So if I write g dash is continuous, I have to put c0. So let me correct that. So it should be c0, and this is of course the same as saying that g is c1 on AB. C1 means is first continuously differentiable. That means the first again I should have written not AB, I should have written CD. G dash should be in C1 of CD. C comma D. Okay. So G is in C1 of CD, means G is first continuously differentiable in CD. That means G dash exists in C comma D and it is continuous on C comma D. So that means G dash is C naught. G dash exists and is C naught. C naught is just continuous. That is the same as G is C1. Okay. So you need this condition, and you also need that G is bijective so that the inverse function is also differentiable and it should be continuously differentiable. So this must be in C naught AB. Okay, and or this is the same as saying that G inverse is in C1 of AB. Okay, so if I write so this is what a reparametrization. So it's the picture is like this. You have this A comma B. on the real line, okay? And you have this parametrization gamma which is going into R2, the image of that tracing the curve that you are interested in, okay? Now this takes t to gamma of t. Now you have from c comma d to a comma b, this is your reparametrization, change of variable. So what you are doing is you are sending u to gu and calling that as t, okay? And the point is that this must be bijective, okay? This must be bijective. So in particular, it means it's 1, 1 on 2, and therefore, there is an inverse map, there is a G inverse like this. So G inverse will take, T to G inverse T, which is U. So there is an inverse map. And you want in both directions, both of them should be differentiable, and the derivatives must be continuous. So this is what is a continuously differentiable invertible change of variable. And that is what a reparametrization should be, okay? That is the correct definition. If you try with the reparametrization which is not 1-to-1, like t equal to u squared for the parabola, or you try something which is 1-to-1 and differentiable like t equal to u cube, still there is a problem because inverse is not differentiable. You don't want all those pathologies, okay? So this is what is happening with in the case of a correct reparametrization. What happens is that in this situation, something interesting is going to happen. What it will do is that if the original parametrization was regular, then the new parametrization will also be regular, okay? And the fact will be that, the regularity of the curve will not be affected by such a parametrization. So, and that is basically because of the chain rule. So you see, what is this new parametrization? The new parametrization is given by gamma of u. Gamma of u is just in the small gamma, instead of t, you put small gu. Okay, and with respect to the new parametrization, what is velocity? Gamma dot of u is by definition, d gamma by du. Mind you, the dot is differentiate with respect to the parameter. For capital gamma, it is u is a parameter, so gamma dot u means d gamma by du, d capital gamma by du. But you see, if you use this, then you see this is actually d small gamma gu by du, and this can be written as d gamma by dt at t equal to gu into d u by so into dt by du into, I should write dt by du. This is just chain rule, and this dt by du is nothing but d by du of gu. So this is going to be d gamma by dt at t equal to gu into, this is g dash u, okay? And so you see, this capital gamma dot of u is this, but watch this. What is this? See, you are getting capital gamma dot of u is small gamma dot at gu into g dash u. This is what you are getting. Now watch. See, if the original parametrization is regular, then this never vanishes, all right? And my claim is that this will also never vanish. The reason is because g dash u will never vanish, okay? And why g dash u cannot vanish is because it is an invertible differentiable transformation. See, notice, see, we have originally a, b to R2, we have gamma, t going to gamma t, okay? Then our change of variable, which is reparametrization, was from CD to AB, which is u going to g of u, which you called as t, okay? And I told you that the important thing is that g dash u exists and is continuous, okay? That is g is C1 on CD, okay? And I told you that this is supposed to be bijective. Therefore, there is an inverse map which is, t going to g inverse of t, which is your u. So there is an inverse map, and I want that also to be derivable. Its derivative should exist, and that derivative should be continuous on AB. So you see, g inverse dash of t is also continuous. Basically, you want g inverse also to be in C1 of A comma B. Okay, but you watch this. What does inverse mean? It means that you go this way and come back, or you go this way and come back. These are identity maps. Okay, so you see, if I start with, so if I go like this, it is first apply G, then apply G inverse. and this should be identity on CD. This should be the identity map on CD. And identity on map on CD means, it's just taking U to U. So basically G inverse circle G of U should be U. That's what it means. Okay. Now you see, apply say the chain rule. What you will get is, what is the derivative of the product? You will get G inverse dash of G of U into G dash of U is equal to, I'm differentiating with respect to U, I will get 1. Because on the right, I am applying d by du on both sides. So here if I apply G inverse of G of U by the chain rule, I will get G inverse dash of G of U into G dash of U is equal to 1. But you see, what does this mean? This G inverse dash multiplied by G dash is 1 forces that both of them can never be, neither of them can be actually 0. Because if one of them is 0, you will not get 1. So you see, this forces that, G inverse dash and G dash never vanish. You see that. And this is if I write if I write this composition. You could have also written the composition like this. If you wrote the composition like this, first you are going to apply G inverse, then you are applying G. Okay, then it will be G inverse circle G is identity now on the AB. Okay, and this means if you write it G inverse of G circle G inverse of T is equal to T. Again you differentiate with respect to T now. You will get the same thing. Basically what you will get is, you will get G dash of G inverse of T times G inverse dash of T is equal to 1. Again this will tell you that G dash multiplied by G inverse dash is 1. So neither can vanish. So this is also giving the same thing. G inverse dash and G dash can never vanish. So you see, what you can understand is, therefore your G and G inverse, the derivatives can never vanish. Okay, and because of that, now look at this expression. See, this G dash never vanishes. Okay, and therefore this capital gamma dot vanishing is equivalent to small gamma dot vanishing, and capital gamma dot never vanishing is equal to small gamma dot never vanishing, because this G dash is never vanishing. Therefore what does this mean? It means that if your original gamma, small gamma, was a regular parametrization, then the new capital gamma, which is a reparametrization, is also a regular parametrization, and this is if and only if. So what it means is that if you take the correct reparametrization, which is reparametrization by bijective, both sides invertible differentiable map, okay, then it will keep regularity intact. By taking a regular curve and you correctly reparameterize it, you will not get an irregular curve. What happened with the parabola was t equal to u square was a bad parameterization. T equal to u cube was also a bad parameterization. That's why you did not get regularity. The original parameterization at squared 2at was good, but it was messed up by t equal to u squared or t equal to u cube, because they were not differentiably invertible transformations. Okay, so this is just to tell you what the correct definition of reparameterization should be. Okay, fine. So now, having said this, okay, there is one more thing I wanted to say. See, this condition about this bijectivity business, okay, bijectivity means that it should be injective and surjective. Okay, I want to say that the injectivity is also kind of automatic. Okay, why is that true? That's again because of the derivative not vanishing. Okay, see, for example, let us look at this CD to AB. Let us look at this map. The map is G, U going to G of U equal to T. Now, what is the condition? G dash never vanishes. So G dash is what? And of course I am assuming G dash is continuous. So G dash is a continuous function on C comma D on an interval. A continuous function on an interval, never vanishing, must have the same sign. Okay, because by the intermediate value theorem, if a continuous function takes two different sign values on an interval, somewhere it has to hit 0 by the intermediate value theorem, which is valid for continuous functions. So if a continuous function is going to never vanish on an interval, it has to be the same sign through the interval. So you see, that means G dash is having the same sign. Okay, but if G dash has the same sign, it means that either G dash is throughout positive or G dash is throughout negative. But if G dash is throughout positive, you know that G is strictly increasing, and therefore it is 1 to 1. If G dash is throughout negative, G is strictly decreasing. Therefore, again, it is 1 to 1. So you see, as a consequence, 1 to 1 comes automatically for you. You understand? So you see, the injectivity part is automatically sitting inside the derivative never vanishing. Now, this is a very important thing. If you go and do some basic analysis or some topology, you will see that there is a circle of theorems called the inverse function theorem, implicit function theorem, and open mapping theorem. So this open mapping theorem, inverse function theorem, implicit function theorem, they revolve on these ideas that, invertible differentiability and then the map being open, and in particular getting injectivity, local injectivity, these are all kind of equivalent. Okay. So in this case, I am saying that injectivity is certainly there for free. Okay. Just the differentiable invertibility is good enough. Okay. So anyway, so let me now go to our question. So our question is, at least we know now that you take a regular curve, reparameterize it in the correct way by a differentiably invertible map, then it will remain regular. Okay. But what is the advantage of this reparameterization? Why does it help us? See, we want to show that there is one reparameterization that will give rise to unit speed. You need that, because only then you can take that parameterization which has unit speed and measure the acceleration and get the curvature, and you can apply your definition. But you see, the point is, why is it that you are trying to do this reparameterization? What is the actual aim? See, the aim is that you are trying to take a regular curve which has some arbitrary speed, and you are trying to change it into a curve which has unit speed. So the purpose of the reparameterization is to modify the speed, and the modifying the speed is being done because you see, what is when I took this small gamma, the speed was norm of this small gamma dot. When I reparameterize it to capital gamma, the speed is now capital gamma dot. And what has happened? This capital gamma dot is this small gamma dot scaled by this G dash u. So this scaling allows you to tinker with the speed. So the question now is, can you tinker with the G in a nice way so that your capital gamma dot has length 1? You see, that's the idea. Can you find a G for which a suitable G such that your capital gamma dot after reparameterization now becomes, in magnitude, it becomes 1. Can you do that? That's the question. And surprisingly, the answer is yes. And what is it that does it? It's the arc length, which is a very humble thing that we have all seen. Okay, so that happens. Okay, so let me come to that. So you see, we are so how does that come? So what we'll do is search. So let us search for a reparameterization with unit speed. So what is it? Your situation is like this. You have AB, you have this gamma which goes into R2. This is T going to gamma T. Okay, and this is regular. And regular means, gamma dot of T is never 0. Okay, and then you are making a reparameterization from some CD to AB, and this is simply, you are sending U to GU. This is your reparameterization. GU is T. Okay, and remember, this is supposed to be differentiably invertible. So this is bijective. There is also an inverse. This is T going to G inverse of T, which is your U, and you have that G is C1 in CD, and G inverse is C1 in AB. Okay, so this is there. All right, and we just now I just told you that we calculated the speed, the velocity of the reparameterized curve. So the reparameterization, this is this capital gamma, which is gamma. So this gamma is capital gamma is gamma of u, and this is small gamma of g of u. Okay, and this small gamma is gamma of t. Okay, so we by the chain rule, you got gamma dot of u is equal to small gamma dot of g of u into g dash u. Okay, and mind you, the aim is you want to get this g dash. I mean, you want to get this g. So what you can expect is that you can get G by, for example, integrating G dash. Okay, or the other way is that you might try to get G inverse. Okay, you can try to get G inverse, and then taking inverse of G inverse, you should get G. See, somehow I want G. There are two ways of doing it. Either try get G dash and integrate G dash, or get G inverse and then take inverse of G inverse, you should get G. Okay, so but what is the aim? The aim is you want this to be equal to 1. So let me write it like this. Want G of u such that you see capital gamma dot of u is equal to 1. You want this. Okay, you want the reparametrization to make it unit speed. Okay, but you see, if you take norm, what you will get is norm gamma dot of u. You take norm on both sides, is small norm of small gamma dot of G of u into, this is only a scalar, so it will be mod G dash u. Okay, so as we assume that G dash is greater than 0, G dash has to be either throughout positive or throughout negative on this interval, since G dash never vanishes and is continuous. Okay, so and of course the advantage of that is then mod G dash will become just G dash if G dash is positive. So then you get this formula. Okay, now so this is so this is one thing, and you can try to get G by integrating this. All right, so you can get G by taking integral G dash u du. Okay, this is one thing that you can do. All right, but the problem with doing this is that you see this gamma dot of G of u, if I have to see what is the right side. The right side is I have to integrate 1 by gamma dot of G of u, and that expression already involves G of u. So this seems to go around in circles because I am trying to find Gu. Okay, so the trick is, look at the other way of doing it. The trick is that actually G inverse is easily accessible. You can find G inverse easily, and once you find G inverse of that will give you G. And why is it easy to find G inverse is because that's connected with arc length. Okay, so I've already told you that you see this G and G inverse are differentiably invertible inverses of each other. So you see G circle G inverse, okay, on any t is t. Okay, you have this these identities. So what this gives is, if you differentiate, you will get G dash of G inverse of t into G inverse dash of t is 1. Okay, and if you write it the other way, for u, you will write G inverse circle G of u is equal to u, and if you differentiate it, you will, with respect to u now, you will get G inverse dash of G of u into G dash of u is equal to 1. So you see, now what happens is, you see this G, see this G dash u is 1 by G inverse dash of Gu. So I'll put it here. So what I'll get is, you see G, so 1 by G inverse dash of G of u is equal to 1 by norm gamma dot of G of u. Okay, and this allows me to write it as G inverse dash of t is norm gamma dot of t by putting t equal to G of u. Okay, and what is the advantage of that? The advantage of that is, now if I integrate this, okay, G, therefore you see G inverse of t is therefore integral from t naught to, let us say, t of G inverse dash of t dt. Okay, and that is equal to integral t naught to t. What is G inverse dash? It is norm gamma dot. So it will be norm gamma dot of t dt. But what is norm gamma dot? Norm gamma dot is the speed. Norm gamma dot of t is nothing but the speed, and it is ds of t by dt, where s of t is the arc length. So you see, if you are moving along a curve, okay, then when you move from t naught to, let us say, t naught, so this is gamma t naught, and you go to gamma t naught plus delta t. Okay, if you fix a point, so if you fix arc length from a from a given point. So here S of t naught is let us say 0. You start measuring arc length from here and you are going in this direction. Then at this point, the arc length will be S of t naught plus delta t. Okay. And what is this arc length? See, the arc length can be approximated by this length. This length is norm of gamma of t naught plus delta t minus gamma of t naught. Okay. And you see that length is, if you write it out in a differential way, it is just so I want to say that this is just delta s by delta t. Okay, because you see this length is so if you write it in terms of components, what is this? Let us write it out. So you see this, see gamma t has two components, x of t, y t. Okay, so you write it in that and use the distance formula. So what you will get is, this is norm of x of t naught plus delta t, y of t naught plus delta t vector minus x of t naught, y of t naught. And the length of this vector is just by the distance formula. This is just square root of x of t naught plus delta t minus x of t naught the whole squared plus y of t naught plus delta t minus y of t naught the whole squared. That is what it is. That is the length of that vector. I am telling you always this, we have this convention when you take either you write vector as position vector of the coordinates, or you just think of it as two coordinates. Then you are supposed to take the position vector of that point. Okay, so there is this dual idea that you should always think about. So, but this is what? This is just delta x. This is a change in x due to t, and this guy is just delta y. And you see, this is nothing but this is the same as if you write it like this is delta x by delta t squared plus delta y by delta t squared delta t. And but what is this? This is exactly delta s. Okay, the arc length is exactly this. Is approximately delta x, delta s, but without when you take the limit, then this is ds by dt. So I just want to say that the arc length, you see, gamma dot is just this is just to tell you that norm gamma dot of t is just ds of t by dt. All right. Or the other way, what I have actually done is that you see, so let me write it here, delta s by delta t delta t. So the other way to write this is ds of t is norm gamma dot of t dt. I want to say that. No, don't. So see, yeah. So when this G and G inverse arguments, when you write it, you will get confused. Please be very careful. Okay. Just focus on what is the variable. When you are writing G inverse, the variable is t and is going to u. So either you write d by dt of G inverse t, which is G inverse dash of t, or you write it as du by dt. Okay. So be careful when you write the derivative of the inverse. Okay. Okay. So you have to be a little bit careful. So here, so you see, this is the arc length. So at the end of all this, you see that what is this? This is just arc length. So what are you getting? You are getting G inverse of t is just this. So G inverse of t is just integral t naught to t of the, if I write this as ds, then I have to change also the limits. It will be from s of t naught to s of t. Okay, and but this is just arc length. See, this is just s of t minus s of t naught. So you see what is happening. Your the reparametrization that will give you unit speed, if you assume that the reparametrizing function is monotonically increasing, so that its derivative is positive, you cannot find that function directly, but its inverse function is directly visible. It is nothing but the arc length. G inverse is just the arc length. Therefore, what is G? It is inverse of the arc length function. Okay. So this implies that G inverse is the arc length function. Okay. What you must understand is that instead of taking G dash as positive, I could have assumed G dash is negative, which means that G is decreasing strictly. Then what will happen is you will get a minus sign, that's all. And you do the same calculation, you will see that G inverse will be negative of the arc length. So you see from this discussion that solving for G, you have only two choices such that G inverse is either the arc length or negative of the arc length. Okay, these are the only two choices that gives the reparametrization for a unit speed curve. So what we have done is in one go we have proved that there exists a unit speed reparametrization. The reparametrization is given by a function G whose inverse is the arc length. So be very careful about this. The inverse is the arc length. And either it can be inverse is equal to arc length with plus sign or a minus sign depending on how you choose the reparametrization to be either monotonically increasing or monotonically decreasing. Okay. But there is only one, it's only the arc length that's doing it. Okay. So we have proved the existence of a reparametrization. Now, so this implies that G exists such that we get a unit speed reparametrization. Okay. Now, now we have the recipe to calculate the curvature using the definition. So what is the recipe? Start with the regular curve. Since it is regular, there is a regular parametrization. That regular parametrization may not have unit speed, no problem. Use the arc length, take the reciprocal, take the inverse of the arc length and take that substitution. Okay. Then you will get a unit speed reparametrization. Now you get a unit speed reparametrization, calculate the acceleration, that's the curvature. Okay. Now after this long haul, you have to show that, okay, if you do this, you really get the curvature formula that we got geometrically first. Okay, we have to prove that. Okay, but at least what we have proved is that the existence of unit speed reparametrization is automatic, it's there. And the key is only the arc length. You have to invert the arc length function. But this is the problem with mathematics. You prove something exists, it's abstract. You try to implement it in even a single case, okay, it will become formidable. Okay, so let me explain that. Okay, so let me write down the recipe. What is the recipe? So our recipe to find the curvature of a curve a regular curve is start with a regular parametrization, gamma of t. So gamma dot of t never 0. Reparametrize. Okay, reparametrize to unit speed. What does that mean? That's what we have just now proved. So put t equal to g of u. So you will get gamma of u is equal to small gamma of t, which is small gamma of g of u, where your g inverse is the arc length function. Okay, and therefore see g inverse is, by the way, you see t is g of u, so g inverse of t will be u. Okay, so t is gu, so g inverse of t will be u. Okay, and g inverse is the arc length function. Okay, so and it's a function, g inverse is a function of t. Okay, so I have to put t here. So let's let me do this carefully. So what you have to do is that basically you have to take gamma of, you see, arc length function of t. This is what I have to do. Okay, this is my my new parameterization, and I should call this arc length function of t, which is g inverse of t. I have to call this as u. Okay, and this u equal to g inverse of t gives the correct substitution, which is the inverse of that, which is t equal to gu. Please understand. It's somewhat confusing at first. So what you have to do is you have to take the arc length function, okay, as a function of t, invert it, that gives you your g, that gives you your g, and you have to put t is equal to g of u for that g. Okay, that's what you are supposed to do. This is the recipe. Now you see what happens. This is terrible to practically apply. So I'll give you a very simple example. So here is an example. Just take graph of y is equal to sin x. I already told you this graph of a function is the simplest avatar of a curve that you can think of. And when you take graph of a function, always it's going to be regular, because the velocity will never vanish. So you see, basically what is going to happen is that basically this is the sine curve. Okay, so if you want, it's going from r to here. You are simply taking, so the graph will be x going to x comma sin x. Okay, that is a graph. The function is from r to r, x going to sin x, but I am taking its graph because only the graph will give me a curve. Okay, so basically what am I going to get? I am going to get, I'm going to get the usual sine curve. All right, and now at any point, what is the parametrization? It is x comma sin x. Okay, and this is your gamma. If you want, this is your gamma of x. Okay, that x itself, the independent variable itself, becomes a parameter. Okay, and what is the velocity vector? It is gamma dot of x. Gamma dot of x is going to give you differentiate. First component is x. You will differentiate with respect to x. You will get 1. The second one will be cos x. Okay. What is therefore what is the speed? The speed is norm gamma dot of x is going to be root of 1 plus cos squared x. Okay, if you think of x as time, okay, then this will be, you can write as norm gamma dot of t is equal to root of 1 plus cos squared t. Okay, and so how will I do the reparametrization? This is my original parametrization. Okay, to do the reparametrization, I have to calculate the arc length and I have to invert it. So what is the arc length? The arc length is integral let me use the variable. T is our this thing, so our parameter. So let me do that. So you will get s of t is equal to st minus st naught. So let me write it correctly. S of t minus s of t naught is equal to integral t naught to t ds, which is ds by dt if you want. Okay, but ds by dt is norm gamma dot of t. So basically this is integral from s naught, which is s of t naught, to s which is s of t, of ds by dt is norm gamma dot of t dt. Okay, and then this is going to be, what is norm gamma dot? I have to integrate from t naught to t if you want. All right, root of 1 plus cos squared t dt. Okay, now this is my arc length function. So s of t is this plus s of t naught if you want. This is my arc length function. Okay, and what is my substitution? My substitution is I have to invert this arc length function. Okay, arc length, the substitution is t equal to gu, where g inverse is the arc length. Therefore, g is the inverse of the arc length function. So what I have to do is that I have to see this. What is this doing? This is giving for every t, it is giving, the arc length function is giving for every t st. I have to invert this. This is the inverse function, and this will give for every, so I will get, so this will give me the substitution, which is going to be t equal to gu. All right, it is u going to gu. That is a substitute, that is the inverse. So what I have to do is I have to invert this function. But you see, I'll tell you, this integral itself, that this integral on the right side, this fellow, so this integral here, okay, that itself is a terrible integral. It's a formidable integral. It is called, if you reduce it, it is called an incomplete elliptic integral of the second kind. Okay, it's an integral which cannot be written in terms of elementary functions. It's already a very complicated integral, and if you want to really grapple with it, you have to do analytic number theory. It's not at all an easy thing to do. It's very hard to invert an integral. Some integrals are very easy to invert. I'll give you a very simple example that you all know. See, if I give you, h of t is equal to dt by root of 1 minus t squared. This is something that you all know, dt by root of 1 minus t squared. You know what this is just sine inverse of t. Okay, so h of t is sine inverse of t. It's very easy to invert. It's just sine. The inversion of this integral is just sine, x going to sine x. That is the inversion. So this is what it is meant to invert an integral. This is an easy integral to invert. The inversion is just the sine function, but this is very formidable. It's not at all invertible in terms of elementary functions. Okay, so you see this this theoretical way of trying to show that there exists reparametrization for unit speed. If you try to practically implement it, it is not going to work. You might encounter an integral which you have to invert, and that may be undoable. Okay, so it's practically impossible to use this. But this is the point with mathematics, is theoretically possible to use this. So the beautiful thing is, though you cannot do any calculations with it in some cases like this, you can still use this definition and this reparametrization, existence of the reparametrization, to get the formula directly for any parametrization, and that formula will reduce to the formula that we originally got geometrically. Okay, so this is the point about the theory. The theory gives you existence of something, so you can rely on such a thing existing, and just with the thing existing and its properties being there, you are able to establish formulas. And finally, those formulas, I am trying to get a formula for any parametrization, which may not be unit speed, but that I can apply. Okay, you take this x comma sin x parametrization. For that parametrization, theoretically try to get the unit speed reparametrization, you will go mad, because it involves, inverting a incomplete elliptic integral of the second kind, which by itself is hard to compute. But with that parametrization itself, you can directly write the curvature using a very simple formula. But the key to that formula is existence of this parametrization and its properties, not that you can compute it. Okay, so what I'm going to do in the next lecture is, I'm going to use the existence of this parametrization and get back that formula for curvature using the any gamma as norm gamma dot cross gamma double dot in the numerator divided by norm gamma dot cube. You're going to get that for any parametrization, regular parametrization, which is not necessarily unit speed. So you see, this is the power of the theory. Okay, so you should appreciate that. So we will do that in the next class. Yeah, and thank you for your patience. Yeah.